Alright, let's try this again. Of course, everything is closed now. And that's going to fuck up the display for a little bit, but, you know, that's alright. There we go. Yeah, LS. LS is a thing. Okay, so, OK.jpg, it looks like this. I'm going to try to pull this over again. Okay. Original with hidden data. Stenography. Now this is completely different. This is using grayscale and then just changing the last bit there, and they even have an awesome write-up, so maybe we'll just do this. When you see an image file, do you just see the visual image it represents, or is it, excuse me, is it possible that there's much more to it? Maybe there's some secret hidden in the image that you don't know. It's already an established cryptography practice to hide information in something like image files. It's called stenography. So if you didn't know that, it's called stenography. What is stenography? It's hiding critical information in an image. It's not cryptography. It's usually just concealing data in a matter of putting it somewhere else that may not be ever discovered unless somebody knew to look there for it in a specific way. Because there's different ways you could do it. We'll create a simple Python program that hides a secret message in an image file without changing what the image looks like. Source code is here, so if you want to play along at home, I do have Python, I think. Yeah, I do. So we could definitely just do this here, I think. Not sure, but we'll find out. The idea behind image-based stenography is a simple image file composed of digital. Now, this is how I learned something. You read it, you try it, you do it, you have fun. You're back. Yeah. Frogger Jr. No, Frogger JB. Usually colors, what is in the picture? Usually the colors of all the pixels. Take a 24 color bitmap image, for example. Each pixel is comprised of 3 channels of 8-bit color. However, the least significant bit in these 8 bits carries very little weight, and therefore even if it's somehow lost, you'll barely notice any difference in the visual of the image. True. So like if you grab that least significant bit of every single byte in the entire bitmap, it's not really going to give 2 shits. Like you'd be adjusting. It would essentially be like we're all colorblind. Somebody super sensitive to color might be able to see it, but grayscale, even better, because it's not going to do much at all. But you see that the brightness is a little bit different. On, you know, this one's a little darker. But if you're just looking at a picture, you wouldn't think, is that darkness a little too dark? Is there maybe a message hidden in the least significant bits? So we will conceal a hidden message in a 8-bit grayscale image, replacing each pixel's least significant bit to store a message. 2-bit generator message for C in message, O equals ordinal C. For I in range 8, yield O and 1 left I, or it by I. So essentially an exclusive OR. Yeah. Well, no, it's not OR, it's a shift. And then shift it by that, and then shift it by that back. First of all, the secret message gets converted to Python generator, which returns 1 bit of the message each time. For simplicity, we will just read the readme.md file and use it as our secret message. If you'd like to hide something else, feel free to change this to another file. Correct, but GMash says not much memory would be free if we just take 1 byte. Means large data requires large image file, right? Yes, there's no way to hide a big file inside something smaller than it. Especially if you're hiding it 1 byte or 1 bit every 8 bits. 1 bit out of every byte. would take you a little while. But hidden message, 2-bit generator. So yeah, this is essentially, so my Python's hella rusty. Let's see what yield does. When you create a list, you can read its items one by one. Reading its items one by one is called iteration. Yeah. To understand what yield does, you must understand what generators are, and before generators come iterables. Oh god. Okay. Yeah, okay. Iterable is a fucking list. My list is an iterable. Okay. Everything you can use for in on is an iterable. List, strings, files. This iterable, these iterables are handy because you can read them side as much as you wish, but you store all the values in memory, and this is not always what you want when you have lots of values. True. Generators are iterators, a kind of iterable you can only iterate over once. Generators do not store all the values in memory, they generate the values on the fly. Okay, cool. My generator x by x for x in range 3. For I in my generator, print I. 0, oh, range 3, so 0, 1, 2. So it'd be x times x for x, so 0 times 0, 1 times 1, and 2 times 2. Is the same, except you used blah instead of blah. Yeah. But you cannot perform for I in my generator a second time, since generators can only be used once. They calculate 0, then forget about it and calculate 1, and end calculating 4 one by one. Yield is a keyword that is used like return, except the function will return a generator. Def create generator. My list range 3. For I in my list, yield I times I. So essentially, the yield of whatever comes follows that you want to do on every iteration of your range. So in here, message is our range for C in message. So every because message is going to come in as either an array of bytes or a string, character array of bytes. And then O is going to be ord C, which I'm guessing is going to return, let's see here, the Python, I can't type, ord, oct, or open ord. Given a string of length 1, return an integer representing the Unicode point of the character when the argument is a Unicode object, or the value of the byte when the argument is an 8-bit string. For example, ord A returns the integer 97. Okay, got it. The inverse is chur. Yep. So let's see. Let's actually, well, let's see if we can just do this real quick. So def blah blah blah. And then hidden message, open, I don't know what folder I'm in. Let's do, this is going to be a good mess, but that's okay. 10 kilobytes. Let's try hiding that in this. Let's see what happens. I mean, this stream, basically, the first one before it was just an idea, throw it out, have a good time. Computer crashed, now we're just going to have a good time. We'll be essentially just screwing around with shit until we learn something or don't. I'm kind of bored and not ready for bed, so it's payday. I do have to order something, so I might do that. if any of you could guess my password based off of my thumb position as I typed it, you are truly a badass. All three of you watching. Best childhood friend. Bank. Damn. Alright, well that's good. What are we doing? We are playing around. Okay, right. Back to work. Everybody be serious. To be honest, I'm not entirely 100% certain what we are doing, but right now I'm doing some copy pasting to see what the hell we're doing. Let's now CV2 I feel like is not defined anywhere, but it's probably an import or something. You know, here's the source right here and the tutorial. Yep, I told you it was an import, damn it. Control C. Bloop. Okay, so pip, exit, Q, E, Control Z, pip, install CV2. No. Anybody remember how to install pip? Fuck it, we'll convert it to Ruby. Open CV, so that's just for reading the images. Range length image for WN range length image, write the image message in the least significant bit. I can totally just read in an image as a binary file, and then HW WN range. We're ending it by essentially, we want to take each byte and then put our message in it. So if it's already a 1, so essentially, let's try this. A equals, this is a hidden fucking string. And let's do unpack. There you go. There's your binary. So there's our least significant bits, and we can go through them one at a time. Bin data. Oh, 1, 2. See, great. We playing a guessing game? No, right now we are going to hide a message in the least significant bits of a JPG, which we pretty much just have to make sure that we are within, somewhere within the header, random offset, doesn't really matter. So let's grab a file, a equals file.open. Let's grab OK.jpg. We'll hide it right in that one. And how this is going to affect it, I'm not 100% certain, but hey, we'll find out. Good heavens. OK.jpg, read binary, f equals a.read. Whoa, that's way different. Kind of want to do this on it. F, I think. There you go. Exif, Ducky, Adobe. There's already, what the fuck? You see that? What the fuck? Okay. So that's cool. What the fuck? Okay. We found some strings, whether they were there for on purpose or not. Who really knows? But you know. Now back to work. Damn it. And what was our? It was bin data. So now f is this, and we can do f dot o. And we want to essentially do f dot unpack. Do we want to do that? No. Let's try this. F dot bytes. There we go. And let's start at some arbitrary location. Well, let's go length. Oh yeah, we've got room. We'll start at some arbitrary location, and then we want to do and bin data O. Damn it. What's binary logic in Ruby? Ruby binary logic operations. Binary operations. Bitwise operators. Bitwise and bitwise or. Oh, you know what? So that's that. Dot to I. There we go. So now we have O. And you'll see that we had a 0, and then that one's a 0. So we essentially want, because we know that our bin data on 2 is a 1, right? Dot to I. Yep, that's a 1. And f to bytes 3. That, so we want to make sure that this is going over to it. So if it's a 0 and ours is a 0, we want it to be 0. If it's a 0, so it would be or. Because then if it's a 1, no. Let's see here. Left shift. Let's see here. So what is it now? It's a 0. Left shift. Right shift. Right shift. Okay. Bitwise not. So does that work? No, because that would be. Let's see here. And how did they do it? They did. Okay, that's fine. Oh. Let's think about this for a second. All right, well, thanks for stopping in. And sorry I didn't read that if you've been gone a while. Let's see here. So let's grab a notepad because we got to think for a second. If we have a number that's a 0 and no, let's just do this. We want to go dot unpack star b star pack dot to s2. Damn it. To I2? No. To s2 mod 8. No, that's not how you do it. wish we weren't starting with a 0. Let's see here. I think this will work. Dot unpack. Okay, that's not it. Dot 2 s dot unpack. There we go. That is not right. Yeah, that's not. Oh, whoops. Duh. There. Dot unpack star b star. That's not a 0. Starting to question this. Is ORD a thing? Sure is a thing, but yeah, that's not it. So if we have a 0, if we have a 0, let's try XOR, because then 1 is going to be 1, 0 is going to be 0, and if we have a 1, problem would be if we have a 1 and we want a 1, because we would get a 0. No, see, left shift doesn't work. Wait, can we just do plus? Wait. Yeah, we can. Duh. We can just add it to it. Just add. Because if we have... Yeah, let's try that. Let's see what happens if we just add. We're either adding 0 or we're adding 1, and then we can go back and just... No, that wouldn't work because we need to know the least significant bit. And I need to figure out how to get that right now. Let's see here. So working with bits and bytes and Ruby. All 2 of you watching, totally awesome. Now see, the problem with this is 2s2 works, but packing and unpacking, CCC. Let's see here. Ruby format string minimum padding. Ruby string to end characters. There we go. Oh. It's literally percent 8s. Is that right? we go. So instead of that, we want %8. So that's padding. No, there's a way to do this. Ruby format string leading zeros. Padding a number of zeros. Oh, there we go. Are just. Does that work? Are just 8 0. Aha! Let's go on to our next one. Oh, give me something. There we go. So yeah, that works. So now we can actually work on that last bit. Because we want to just set it to whatever ours is. So 2, 3, 4 is where we'll start, and we want to do bin data dot times do g f dot bytes 234 dot 2 s2 dot r just 8 0. This would be, oh damn it, f dot, I need to cancel this. Let's copy this real quick. Whoa. Hello and welcome aboard. We are going to try to hide some stuff in some random least significant bits at arbitrary places and images and see what happens. We're really just goofing around at this point. Control C. Okay, we're starting over. I need to know F. This. There we go. No, that's not right. Dot 2i16. There we go. Let's see, what was it before? 4. So not exactly. Four dot 2 s2 is that. It's 4, and then if we 1, 2, 4, if we add 1 to it. Yeah, I think what we really need to do is just grab that, and then -1 is the last bit. Equals, let's try this, bin data, oh, 1, 2, there we go, 2. So So then if we grab that, two three eight dot 2s. Two. So let's go G equals G -1, bin data is that, G 101, then we would put it back in there. Yeah, that'll work. So let's put it all together. Let's grab a notepad so I don't have to type a bunch. So essentially we need bytes at 2s2 -1 G equals f dot bytes 2s2. This will probably fail miserably, but hey, you know, it's okay. This is bin data dot time length dot times do f, not f, y. G equals f bytes 2s blah, and then we go G -1 equals y. No, bin data y, and this would be plus y 234 plus y 2s2 G blah that equals bin y, and then we do, because then we need to go G dot 2i16 2? Ah, damn it. Would it have worked before the way I thought it was going to work? Because if so, I can stop being an idiot. Dot 2i2. Yes, it works just fine. 0 1 2. That's 4. Fuck me. Okay, so grab that. I like the way that this one works or looks better. So bin data length dot times, and then we would do f dot bytes y equals f dot bytes 234 plus y dot 2s are just 8. Wait, we still need an intermediate. Yeah. Yeah, I don't know what I was thinking. So G equals are just 8. I like the way that looks. We don't have to do that, but that's what we're going to do. And then G -1 equals bin data y. And then f dot bytes, essentially we just put it back in, equals G dot 2i2. And let's put some of these in there. And so first, let's go bin data dot length 248, and let's go f bytes 234 dot dot 234 plus 248. These are our initial bytes, and we'll go init bytes. And then from here, let's go ahead and run this bin data length dot times do f dot byte G equals f, and then we're putting them back in there. This might crash and burn, but who really knows yet? Sorry to hear that. That's not good. I don't know where that was set. I don't know what channel that was on, but was it here? No. Okay, let's run this and let's see what happens. Alright, it finished. Now let's look at our A bytes. And you'll see 0000435. Do these equal init bytes? They do. So we didn't do anything. Let's do PG, PG, P. Oh, pff. Stupid. So we need something that holds all the bytes first. We'll go like this. T equals f dot bytes. There. So we'll use T, not f bytes. T, 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 and before I do this, let's just grab those out of there. And we'll do this again. Damn it, Control C. I'm going to grab my init bytes, and this will be T. And then our A bytes we will grab in a minute. So now let's paste that. A bytes. Aha! There we go. So we have successfully changed them. And you'll see that A bytes equal init bytes false. And if we reduce them, so if we go A bytes minus init bytes, you'll see that's how many of them actually changed. So we only changed that many using the least significant bit. But the real trick, let's see what it looks like. So T is now this. We need to do pack star. There we go. So, and then let's do T, not T, but Y equals. And then do C equals file dot open out dot, excuse me. And that's going to be for write plus. If it doesn't exist, create it. And then let's do C dot write. Was it Y? Yeah. Y. C dot close. And let's see if we have a valid JPG. We don't. We can't open this file. Let's try going down further and see if that just doesn't break it. The biggest issue we have here is with JPG. Now with the bitmap, this would be super easy. With the JPG, we have to avoid FF. I don't really want to test, but we could. So for POC, proof of concept, let's go ahead and open this in Paint, edit, file, save as, a bitmap. Well, sure, just give me a, there we go, 24-bit bitmap, sure, why not? And not there, desktop. Interesting. OK.bmp. Okay, so let's go ahead and I need to copy all these out of the fucking console because going up like this is just. So let's go like this. And let's go like BMP f.read We could chain that, just put a dot read there, but I don't want to because it's messy. We're not doing that. And I think that's all we needed, really, except the T, which is down here somewhere. T equals f dot bytes. There we go. Now let's do C equals file dot open out dot bmp write plus C dot write T dot pack. Did I forget to pack it? Or did I pack it? I think Y was packed, right? Yeah, Y is packed. So this will be T dot pack star C star C dot close. So this should work. Let's see. F dot byte. Now, of course, it's much bigger now. And then bin data dot length dot times do, still with the same offset 234 plus Y. Bloop, bloop. And then file open, let's write that. And look, we definitely affected it. Quite a bit. Most likely if we shift it by like 1 or 2, we won't have that problem. So let's try that again, but instead of 234, let's try 235. 235. Oops. Definitely doing stuff. Let's try 236. One of these might work, or we'll have the same exact results because I did something wrong somewhere, which is more than likely correct. I didn't fix these, so that's what I need to do. Stenography. It's funny that it's shifted. Let's do Y. G equals that, G dot 2I2. Oh. This right here. No, yeah, that's a string to string. 7? Actually, let's go like real big. 1, 2, 3, 7. I mean, that's still not real big, but not f.read, but there. Put a nil at the end of that so it doesn't read everything out. Let's go like this, and we'll delete that. And then let's go, I mean, we've got lots to work with here, so let's go even bigger. You see that ours are not changing by much, but the original is much different. And currently I'm not entirely certain as to why. I must have something incredibly wrong. Or it's the fact that it's 24-bit. Right, so it'd be Y. Yeah, so we need, so we could do this differently. So let's do this. Save as. If we do monochrome bitmap, okay, 1, okay, oh god, why do I not have 8-bit grayscale? File, open, file, save as, 16 color. 8-bit would be 255, but it wouldn't be grayscale. I'd have to set it to grayscale. Let's try this, just for S's and G's, brah. Alright, so let's try that out. We're going to reduce this by a bit, just for fun. There we go. And then you'll see that our output, so where's OK1? There's OK1, and there's our output. You see we got a little bit of a wiggle right there, but nothing like before, and that's due to the size. So to circumvent that, so 16, if we do Control Z, no, we gotta go file, open, okay, and if we were to file, save as, for example, 24-bit is, well, obviously not 8, it's 3 times 8, so we need to grab all 3, and let's see what that looks like. So let's go ok.bmp, I think that's what it was called. Okay, we know that that doesn't do it, but we'll do t equals bytes, and then you'll see we got to grab 3. So we want to skip and do every third one, and that's going to be this plus y times 3. I think, but we got to make sure that we're starting on the right one. So let's T137. That's 138, 39, 140. Let's do this. 1200 dot dot 1220. Okay, so 233, 233. So it looks like 201. Yeah, 201 is this one here, and that's the least significant. And then 1 plus 1 would be times 3, so plus 3, and so on and so forth. So 2301, 2301. Let's see what we get here. Out.bmp, and it's fucked. It's exactly the same amount of fucked. Do we need to modify each one of them? Let's try that just for the hell. Wait, is this math right? Let's try this, because I think this starts at 1, which is not going to get us where we want to be. So if this starts at 1, then we would technically not be in the right place. Let's see here. Let's do 4 dot times do t o p o and it starts at 0. Okay, so 01 is correct because this first one's going to be 0 times 3. And then it would go through. That'd be 1 times 3. I could be backwards on those. So let's do this actually. Let's do 4 dot times do O, and then let's do T plus O1. Damn it. O. Not T, O. O times 3, and we want to put dot 2s 2 end. Well, that doesn't look quite right, because if we think of it as this, O equals 0, 1. What? 2. That's not right. T 1201 dot dot 1203. Yeah, see, that's not right. Oh, right. I'm stupid. 6. Yes, that is correct. So it'd be 0, 1, 2. Let's try 1202 real quick, and maybe I'm in the wrong spot. This should be correct, though. It's definitely not correct. You know, I think what we do is y 1202, that's the first one. And then we'll do y plus y. And then yeah, so we do 3 times would be 0, 1, 2. So 3 dot times do u. This would be plus u. Y plus u. Big data, bin data divided by 3. No. Now, how do I want to do this? Bin data dot length divided by 3, kinda. Close. So we need one more character in our fucking binary data, which is way the hell up there. I passed it. damn it. O dot length. That's our problem. Fucking dividing by 1 and shit. Yeah, the worst case scenario was we'll lose a character, and for testing, I don't care. So we're gonna do that. We're gonna do bin data O dot length divided by 3 dot times do Y. There we go. And then here we do 3 dot times do U, and that's gonna be Y plus U. Y plus U, Y plus 2, 1, and then 1, 2, 3. Alright, fuck that. Let's just do CNT equals bin data O dot length while CNT is greater than 0. Let's see here. I'm sure my syntax is wrong there. Ruby while. We've lost everybody. That's okay. I'm just having fun. Wow. Okay, yeah, there's no do. Duh. Okay, let's just go x is 0 while CNT is less than 3 dot times do U, and then that's going to be CNT plus U, CNT plus U, CNT plus U, and then CNT plus equal 3, right? Because if we're starting at 0, position 0, then we're going to go that position, second position, third position, and we will be equal to, so 0, 0, 0, 1, 2, and then we want to start on the third position, so 3, and then we'll go 4, 5, 6. Yeah, that's correct. So we'll do that. Bin data length, CNT plus U, CNT plus U, CNT plus U, 3 dot times do, CNT plus equals 8. Let's see what that does. Ah, son of a bitch. No implicit conversion of nil into string. What? G bin data O. That was probably the problem the whole damn time, really. And that's gonna be times block and IRB 3 dot times do U. Can this not see that? .293 is here. G is this really not coming out to be something? Okay. Let's do that, and we'll also PCNT. .255. And let's grab bin data o.length. -1. Oh, there we go. That's how it's done. Alright. And it's exactly the same amount of fucked up. Delete, delete. Let's make sure we're reading the right file. Okay. I think something's being filtered out somewhere. This shouldn't do anything different. It doesn't. So let's pull open HXD and take a look at this. So we are starting at some arbitrary number, which is 1201 calc 1201, which is 4B1. Oh, 4B1, which is E9. And let's see here. So these are all repeating. E5, E9, 9E, E5, E9, 9E. So we are at E9, which was 1201, 1202 would be here, but these are likely, can we, let's do this, because what we're doing is we're changing this from 9E to 9F, and you'll see what happens here. If we go like this and go -X, 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 this is probably going to yell at me. .2 I16 wait, .2 I, no, unpack, there you go. So here's the characters, 229, 233, 158, and we're changing 158 to 159. And if we go -1 plus equal 1, so let's go W equals W -1 plus equal 1. So now we have that, and if we pack that, you see E5, E9, 9F, but really what we want to do is treat that as one number. And so that would look like OX E5 E9 9F, I think. Plus 1 is that, and then dot 2 S16. Ah, you son of a bitch. Yeah, like this. E5 E9 AO. To move it 1. So what we want to do instead of doing these in 3s, we want to grab 3. We want to do bin data.length dot times do D. Sure, why not? Let me come back over to chat. I'm sure nobody's watching. Yeah, one person. But yeah, if you are having fun watching, great. You know, we're just writing some code here. Just playing around, writing some code. So it's not really reverse engineering. We're just thinking outside the box, warming up the brain, making it think about, you know, how would we want to do this? And we're doing it in Ruby, which is probably people's biggest gripe that I'm not doing it in Python. But whatever. I have Ruby available real quick. So we need to make sure that we're starting at the beginning of one of these. Which would be right here. Although that 9D and 9E, maybe we just picked a really bad spot to start. Like, let's... And these ones start... EO D671, EO D671. 1D70. 1D70. That's going to be 7536. 7536. Plus D, that's going to be, we have 3 bytes. I gotta figure out how to go from because we can go pack C and then we need to go dot to I16. No. 2? No. We have this, we need to put them all together as one value. Oh, that's just stupid. wait a minute. Let's see here. Nine E. No, yeah, we're getting the same answer. E5E9AO. Dot 2 I, that won't work. It'll just be 0. F won't work. Dot unpack C. So we're starting with this, and we're saying pack C, but we're saying +1. Yeah, it's correct. So our code was working just fine. Plus D. And D times 3 would work just fine. Do this just for good measure. 2I. Wonder if our RJS is fucking us up. I doubt it, but we'll do this. Get rid of that. Get rid of that. Bin data length that too. Okay, let's see. And T. No, that's just going to be D. Yeah, it's just D on that. I think it has probably something to do with our packing. So you notice that everything gets shifted off a little. Like, well, let's do this. Let's take a look at what address was that? That was 1D70. Let's open this. Go to 1D70. We're going to put that at the top. 1D70. Put that at the top. 01. 01. Yeah, we're literally only changing every third one with our bit. And we're doing it only that far, really. So let's try starting somewhere like right here. Now, yeah, let's start at 2051. 2051. And let's change that to a 9F. Now, that didn't screw with anything, but it was also only one. So let's go. Yeah. Ah, you son of a bitch. It's not opening Paint. Apparently it is. values. I can't read. 2. There we go. So, okay, 2. Is there any difference in this versus this? Okay. So, let's start at, what did I say, 2051? Clear 2051 is 8273. And I do want to try something because I am stupid. Right, binary. That might be the cause of all of this. What do you know? I'm just stupid. Don't forget to tell it you're writing a binary file or it will screw you over. It'll ignore white space and stupid shit like that. So we now have in here our, wait, yeah, that's out. And here's OK. So let's close and close. Let's open up OK. Let's open up out. We'll go to 2051. Go to 2051. Scroll those up. And you'll see 9E, 9F. We've changed those. We've done it. I wonder if this will work with the JPEG now. Just changing some random shit in there. Let's try it. Of course, now that this is completely different, let's make another copy of it and just put it down here. And let's do OK JPG. Don't forget to write binary. Gah! Stupid. Stupid. And let's change every other third one, but let's start much lower at like, well, let's take a look. Where do we know is going to be safe? Somewhere down in here-ish. EEO. 3808. And then we will also grab a, we'll make a decoder as well, so that we're not leaving everybody hanging here. Out JPG, okay, got it. And every third one, sure, let's try it. Every third one might be a bad idea, but maybe we'll get some fun outcomes here. Okay, that definitely broke the f*** out of it. And you can tell where we started writing. Let's try not every third one, but just plus D. Yeah, it's still borked. A little bit differently borked, but at least we have a valid JPEG file now. It's not. Now we could probably get away with something like change every 256th, but we'd probably run out. So let's do change every 16th. Could probably get away with that. I'm not saying for sure, but we could probably find a number that would work. Yeah, we got some different colors now. Still not good. Let's bring this down a lot. Actually, let's go up a lot. Let's go like 5808 and times 32. Hopefully we don't run out of space. I don't think we will. Yeah, we didn't. And you'll see definitely not what we're going for, because we're modifying one of the, most likely the FFs and the little tags. We're hitting the key of it. Let's go like 15. We shouldn't run out of space. Actually, let's go like 9. And we'll do 255. Yeah, we ran out of space. Trace call to, yeah, we ran out of space. Let's drop this to 808. Should be okay, right? Okay, forgot to close the file before I wrote it, but okay. Let's try that again. That borked it. One 808 and 120. Oh, it just isn't seeing it. So you see we got some random changes all up in there. Really random changes. Let's go with an arbitrary 7. I like 7. Hey, kind of close there, you know? We're only screwing it up a lot. Even better, you know, you're getting closer. You know, if we screwed with this long enough, we could calculate these things. But let's go back to the bitmap, because that's a lot more impressive. I'm sure you can agree. So we have an out.bmp that looks exactly the same as our OK.bmp. There. I mean, can you see a difference? I can't see a difference. But our message is in there. But now we have to find it. So essentially we'll do the same thing but backwards. We want to grab that least significant bit from, so this is our code up here. Let's get a proper tool here. Excuse me. Nope. Good heavens. To Betsy. Okay, so this is encode. And we want decode. And this will be out.bmp. Out. And this is going to be msg.text. No MSG. And essentially we're going to read, grab the bytes, and now this we don't know. So ideally we would put somewhere in there that length. Let me see what that length is. We're going to cheat for now, and then we'll come back around to that. 256. How suiting. And 255 should be our last character. Yeah. So 256 times. And we're just going to use that same loop because we know it already. And times do, and we want to start here, .2s, and then essentially we want to go before this, we want to go MSG equals that, and we'll do MSG plus equal this last character. And we don't need this anymore because we're not replacing it, we're just reading it. T.pack, and this would be MSG. So let's see what happens here. So let's grab this and do that. Okay, here we go. MSG, dot pack star C star B. Oh right, we need to go MSG dot pack star star. Is that right? Aha! What do you know? So this is a hidden fucking string. We did it. And it would be pack star B. And this would be MSG. Now, in code, let's do one thing more. We need to go, not bin data length at times, but we need this as a variable. This is going to be message length equals that. And then that obviously 256, so message length dot 2s2. That's correct. So the first chunk of our string, the first 8, 1, 2, 3, 4, 5, 6, 7, 8, looks longer than 8, but that's only 8. The first 8 will be, well, let's say the first 16 would be our length. That would give you up to, well, let's see here. If we do this plus that many more zeros, 2, 3, 4, 5, 6, 7, 8 dot 2 I2 65536 size. Now, of course, that's going to require a pretty big file because we're only modifying every third byte. Let's try not doing every third byte. Let's try doing just right in a row here. So I have the good stuff saved, I think. Yeah, I do. So let's do just like this and see how that affects it. Because now that I think we have it correct, now that we're writing it properly, I think we'll be okay. Yeah. See, I mean, out.bmp versus ok.bmp. Oops, not that one. I mean, I can't tell one lick of difference. And if we look at those in HXD, close, 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 out, okay, and we were at 8 8273. 8273 is 2051. Scroll that up. Yep, we're doing exactly that much, which, granted, yes, that takes a bit, but we're not noticing any difference. So that works fine. So we don't have to do every third one to do the least significant bit. We're going to do the least significant bit of each color. And if you wanted to really make sure that it was hard to be seen, do it on green. So it's red, green, blue. Do it on the middle one, which of course you would just start on a green one and then do every third one, because human response to green is not that great. So this is encode every third byte. Encode each byte. And that's that right there. So let's get back to our, I'm using this because it's got bigger font so you can see it. I could change that, but I don't feel like it. Where did I start doing it? Oh, message, I started here anyways. Can I just control C? Oh, look at that. Bloop. Message length equals bin.data o.length. And then this would be message length dot times do d. We're going to stick with this for now until I'm done. And then from there, so dot length dot times d, and then we want the first 16 would be our length, yeah. So message length, I was gonna put mlen bin equals message length dot unpack, right? Nope, that's not it. I think it's just 2s2. Yeah, there you go. Inline bin is that. Go away. 2s2, and then so message length dot times do d. Essentially, we want to just add that to add this length to this, and we want to do mlen bin dot length. Now, yeah, that's correct. Plus message length dot times do. That will put the first 16 on there for us. Oh, we need to .2s do the whole thingarooski .rshift .rshift a 16 with zeros. Is that right? Let's check it. Nope. What was it? I know it was something like that. R-just, not R-shift, R-just. Right, justify. There we go. So 256, 512, 1024, 204, 8, 4096, 906, I don't remember, yeah, and so on and so forth. One more, and then 65535. Well, 6 technically, but yes. Yes. Let's see here. Okay. So that's that. And the length is always going to be 16. So we don't have to do this fanciness. We'll just do end length plus message length plus 16. And then bin data equals mlen bin plus bin data. That will put it together for us. So now it's just going to start, which means we can just do bin data length dot length, and then bin data od bin data o equals mlen bin plus bin data o. Is that correct? Bin data, yes. So now we have it on there. So don't run that because I've already done it. Bin data dot length dot, we don't need this. It wouldn't hurt, but we don't need it. So now we're going to put our length on there first. Message equals, what was our message? It's like, this is a fucking hidden message or something. I don't know, we'll come back to that in a second. Message equals, I think it's just, this is a fucking hidden message, like that, I think. That's what we're gonna call it for now. And then bin data equals message dot unpack star b star. Sorry, the chat is down right now, so let me grab that just in case anybody's still watching and has any questions. If you have questions, feel free to ask, please, because right now I'm just talking to my computer, which is nothing out of the ordinary, totally just what I do sometimes, how to learn, you know. Message length .2 as are just, we add that to it, good, and then we are going to write those. So we did this, we have the new bin data length times, and then let's grab our original. Just you go away. You come down here somewhere I can see you. Bin data length times do out.bmp. Let's see if it works. And this is on every third. Out.bmp. No discernible difference. Exit. Now on JPEG, I would want to do this in the what's the name of the table? The one for the qualities, and just adjust those a little bit, you know, the least significant digit of the data, and it would be in a zigzag form actually. So we'll look into that in a minute. But and there's great video from Computer File that explains JPEG compression. So now if we open that up in HXD and go to there, we should see 0, 0, close, out.bmp, k.bmp. E, so why are we starting with a 1? Oh, no, we're not. 0. Gotcha. So 0. I don't see anything else changing. What the I broke it. Oh, that's why. Bin data length is 1. See. Bin data O dot length at times 2. So let's close the. Oh, I didn't need to close that, but okay, whatever. Okay, so now let's make sure we still have no discernible difference. Nope. HXD, boom, boom, Control G, go there, scroll them up. Okay, so now we have things changing. Good. And the first one, you see, is all going to be zeros for a while, and then we have a 1, and then some zeros, and then our other bytes start. So good. Now we know that our decode, if we were to run our decode, out WMP, this is not gonna be correct, and you'll see why in a second, because, well, I'd be cheating for one. I don't know. This is can we edit games images by Ollie? Yeah, or resource hacker, or just figure out where the resources are at, and then you can do it there. 272. So now MSG, you'll see, is this, and if we, which is correct, but you'll see that if we do this, oops, damn it. Oh yeah, it's not that, it's this. You'll see that we have 0100, which is our length. This is a hidden fucking string, which I want to grab that for future reference of up here. It's not message, it's string. There we go. Welcome back, Soda, by the way. Welcome back, anybody else who took a break, wanted to have a good time. So essentially what we need to do here is, we don't know some data, but we know that we always start at the arbitrary blah right here. So we know that 16 dot times, so we want to start up here and go message msg len equals this, and then we want to do 16 dot times do, and we'll just reuse d here, and g equals, we'll do this, and that's there. And of course this is going to be plus 16. Thanks, man, I late today, sorry. The first half was a little bit more interesting, and now I'm just kind of writing a little program to hide messages and or binaries inside images files. And here pretty quick we will be to the point where we can load a file into an image, view it, and be like, this looks like a normal image. So we're getting there, we're almost there. So this is going to be 16 more, which would be 89, and we know that. No, it wouldn't be 16 more, because we're doing every third, so it'd be 16 times 15 times 3. 16 dot times do y py puts y I just want to do py and 15. So 15 times 3 be 45 more, which we want to go here. Go 45 plus 8273, 8318. That's where our message starts. How long did it take you to know the image's structures? I looked it up. A long time ago, I learned bitmap, and bitmap is super easy. It's essentially, so 16-bit is 3 bytes. Well, kind of like it. Yes, 24-bit is 3 bytes. 16-bit is 2 bytes. Misspoke. And then 8-bit is 1 byte, and that tells you how many bytes are used for a pixel and how they're split up. For example, in 8-bit, you get 255 colors, well, 256 technically, and you're allocating 2468. So you have 3 colors. It would be 3 3, and it's probably 323 or 232. I'd have to look it up again. Usually green is lower because we're more sensitive to greens. And then in 2 bytes, it's split up again. And then the easiest one is 24, or is 24-bit, which is 3. Compressed images, you realistically need to look at which bytes you can change. But what you do is you look up that file format and you learn how they work, and then you can see, okay, well, in JPEG, if I change the compression table, it probably won't affect the image too much because I'm just changing 1 bit. Like RGB 255, 255, 255 as, no, close. 255, 255, 255 is 24-bit, that's 3 bytes, and that would be FF, which would be 101010. And so it would be a 1 and 7 zeros, 1 and 7 zeros, 1 and 7 zeros. And that's why 24-bit is actually pretty easy, because you have 3 colors, you got 3 bytes, 1 byte for each color, 0 through 255, 0 through 255, 0 through 255. Great, it works out wonderful. So RGB 255, 255, 255 actually just converts to hex. It goes FF. And let's jump back into it here. So message length 16 times that do, we got that, and then we need to go length mlen, we'll call it, equals. So first let's do this. So let's open up our out, grab the message length 16 times that do. Great. So message, oh damn it, I put it in message. This is gonna be message let's do message bits. So this one can be message len. There we go. There, so now message bits equals this, which if we do dot, wait, we gotta go like this, and then dot pack, no, dot, wait, is it pack? Wait, can I just do dot 2i2? Yes, you can. 2i2. So that's cool. So then we can go message len equals message bits dot 2i2, and then we go message len instead of that is here. Message. So now, this is a real test. Let's see if we're in the right place to get the right shit. Message. Fucked something up there. Oh, message len length. Ha! Whoopsie! Don't need that. There we go. Damn it. Okay, what do we get? Undefined method times for string. What? String? Oh, I forgot to run this. There we go. So now MSG equals that. And hopefully, if we dot pack star B star, nope, we're not in the right spot. So how far off are we? Let's see here. Our message is bin data. Bin data. That would be 16 dot dot negative 1. What? Oh. Oh. There we go. Is that right? So we want 1, 2, 3, 4, 5, 6, 7. That would be 15. There. And now if we do this, pack. Wait. Did I fuck it up? Or is our message supposed to be pack star star? Oh yeah, it is 16. So that's that, and then we go message length equals ben data o dot length, mln blah ben data o equals, so copy, paste, and this should give us that with 16, and then it should actually be 16, and then that dot pack star b star. Yeah, so message, let's run message, and that's going to be our decode, which is down here. Yeah, we're off by 1. Message 1 dot dot negative 1 dot pack star b star. Yeah, so we need to go forward 1 bit, or yeah, just like this. And then this right here, message pack B, should be it. No, wait, was I off by 1 the wrong way? What the fuck is that? Something's gone haywire. Let's go like this. A dot close. Oh, we can't be off by 1. We have to be off by 3. Derp. This is gonna be fucked. Yeah. So let's try moving up. It's probably 2-1, but. Huh? Oh, I just wrote it. MSG. 2-1. Just grab to here. There we go. Now, oh, I could have written it by now. There we go. So now this will work. And the first 16 bits is our length up to just over 6 kilobytes. 65535 divided by 1024, 63 kilobytes. So there you have it. Now the fun part, let's see if it works. Let's get rid of let's convert it to each byte. So let's get rid of this, decode, let's put some separators in here so we know what the hell we're doing. Message, and let's get rid of that. Let's get rid of that. And let's see if this works. So this is a hidden fucking string. So fuck off. There we go. So let's open OK, which is our original. We get a message. We're gonna unpack it. And let's see where that gets us. Is my microphone still working? Always have to check. Yes, it is. So fucking string, bin data is this. Message length is bin data o.length, and lang is this. This is going to be our encoded length, which is that, which is 368. And then bin data o equals mlen ben plus bin data o, which gives us this. First 16 has that. Length.times.do this. File.write out. Let's just do this. Close. Out.bmp. Can't see a difference at all. And let's messages here. So now let's the real test out.bmp, and let's actually do that again. We'll do out2 just to make sure that we're doing a different file. Out2, cool, looks great. And we're going to decode out2. We want to remove this. And now this is where this comes into play, because we're not doing every third. So it would just be plus 16, which would be 2, but that'd be 0 up to 15. So it'd be plus 15, which would be 8, I think. I could be wrong on that one. So A, file open that, message bits. Let's see where we're at after message length. $368. So far, so good. And then let's message. Let's see if we're in the right spot or not. I think we're off by 1. Pack, nope. Pack, star, B star. We are off by 1, because we should go 8, 9. Let's run this one more time. There you go. And let's make sure it writes to the file properly. And message that text. What do you know? And the cool thing is, this file is 2.16 megabytes. The original is 2.16 megabytes. We're not adding anything to the file. We're using the bits that are already there, and we could even use, you know, each word if we wanted to do words, but that would be a whole different ballpark. And you probably still wouldn't at all see much difference. So now let's turn these into something decent. So let's do def encode. This will be file path and message file. File path and message file. We'll do file open, and that's going to be file path, not in quotes. Message is going to be message file, and let's try something. T equals file dot, and you know what I should do here is do a dot close. File dot open message file, and that's going to be read binary. Don't forget that. And then message would equal t dot read. However, let's do something here real quick, because what we need to do is test it. So let's go, what variable am I using? T, wait, T is already used, isn't it? Yeah, T is already used. You should use proper variable names. PL. PL equals file dot open fjlj crack me 4.exe read binary, and then message equals pl dot read. No, that's not message. Well, kind of. I want an intermediate variable for now, so we're gonna go rr equals pl dot read. Then we want to do rr dot unpack star b star. Is this? Yes. That works. And message. Oh yeah, that is correct. Message equals, because this is not going to be here. So we go message equals pl dot read. Of course, now I can't read it because I already read it. So let's go pl dot close. File open blah. And message equals pl dot read, pl dot close. And then bin data equals message to unpack star b star. And then message length, bin data o dot length. It's a little bit bigger than 65535. So easy solution would be rjust 32 would get us real big, because that would be 2 raised to, not XOR, what the fuck, decimal, yeah, we need scientific, 2 raised to the 32nd. That many bytes, which we divide by 1024, divide by 1024, about 4 megabytes, which is too big. So let's just do another 8, which would be 24, which is suiting, which would be 2 raised to the 24th, divided by 1024, divided by 1024, which is about, wait a minute, what? 2 raised to the 24th, divided by, that's bytes, kilobytes, megabytes. Wait, what did I just do? 2 raised to 32 divided by 1024 by 1024 bytes to kilobytes to megabytes. No. I'm stupid. Because somewhere in there I gotta divide by 8. Let's see here. 24 bits. Two. Because there's 8 bits in a byte. There's 1024 bytes in a kilobyte. So if we have 32 bits divided by 8, that's 4 bytes. Wait, let's do 24-bit max value. If we have on and off, why can't I fucking think right now? Somebody save me. Yeah, it is. So 2 raised to the 8th. 256, yes. Okay, so 2 raised to the 16th is 65535. That's the maximum length, so that's the number of bits divided by 8 is this many bytes divided by 1024 is that many 8 kilobytes. So 32 is actually not bad. 32 divided by 8 divided by 1024, that's bytes, kilobytes, two raised to the 24th. I think this is right. So this is the number of bits divided by 8, number of bytes divided by 1024. That's kilobytes divided by 1024. That's 2 megabytes. So 24 is about right. Oh god, that was stupidly hard. Not really, you just had to calm down and think about it. Like, stop freaking out, man. Just think. So 24. And then this one would go up 24. Well, let's think about that for a second. It was our just 16. Now it's 24. So this would go up 8, which would be 81. And we can test this in a minute. So, alright, there we go. What is it? Message length, been dated at length. Okay. Let's do this. Copy that. Okay. 24. And if we were to take mlen bin dot 2i2 80920, we're good. We're going to add that to this. Of course, we would be good coders and account for this. There we go. So we've added that. And then, wait, we don't modify this one at all. Nope, not this one. This one. So let's not get into that yet. Out 3. Ooh. Bin data length close. Control C. Let's see what happens here, boys and girls. This one is going to take significantly longer, not. Out 3. It looks completely ordinary, and we have an executable in there. This executable, which is only 10 kilobytes. So now in here, not 16 times due, but 24 times due. And then this goes up by 8, which would be 97. So let's try that out. 3, and then we'll come back and fix this. Let's see if this gets it right. $81920. Whoa. Let's see if this gets it right. EXE. Okay. And let's write that to message.exe. And let's compare the two. MZ cannot be run. Look at that. That's an executable. Everything there, lossless hiding. And our images look, I mean, do you see an executable in there? I don't. But it's there. Why is nobody excited about this? This is fun. I'm going to call this hiding files in images. Yeah, Ruby. Okay. So back up here, we have file. It opens it, it reads it, it packs it. Message file, good. And this is def and code. Writes file, we need to put an end, and then grab all these, do that, and let's do language. Let's put a thing right here and do language and do R or Ruby. Oh, that's so much better. We'll do one of these right there. Def and code, path, blah, 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 blah. Decode. And that's going to be def decode. This is going to be in file, out file. Open up the in file and this message file. File open PL. Okay, this is going to be what we're doing, what we're saving, and this is going to be out file. And that would be here. In file, out file. We should probably cut these numbers down a bit. Like a lot of bit. Like, what's the BMP header size? Bitmap file header is 14 bytes. Extra bit mask, color table, bitmap file format. Where does the image start? Extra bit mask, color table, pixel area. That's what we want, and that's gonna be. Okay, so there's a color table, a gap 1, variable size, and a pixel area. Bitmap file header. The size of the BMP file in bytes is at 02. So if we look here, and we go all the way to the top, 02. And that is the size in bytes, and it's 4 bytes, so those 4 bytes give us our size. And if we go over and do programmer hex 969B2200, divided by 1024, divided by 1024, we get 2.4 divided by 1024, or roughly 2 megabytes. And then actual value depends on the application that created the image. Okay, OA here is 4 bytes. 1, 2, 3, 4. And the offset, starting address of byte where the bitmap image data pixel array can be found. And so that is at 3.6. So we could grab this and then go to 3.6. That's the starting of the bitmap. So pretty much it doesn't matter where we go, but we want to be like, you know, somewhere, you know, since we can have variable sizes, we'll just pick AO. You know, I mean, if each one of these is a pixel, even a 2-bit file, or yeah, like that's 1 pixel, that's 1 pixel, that's 1 pixel. Like, we're gonna be pretty safe even up to here with bitmaps. But let's go with, I like A. Is that a, oh, it's a DO. Yeah, I like AO. We're gonna start with AO, which is 160. Okay, so 160. 160. Then we start at 160. Now the difference between these two, let's not screw it up, decimal. 8297 minus 8273 is 24. 160 plus 160 is 184. I feel like I screwed that up because I don't recall it being so simple. Is this the same number? Was that the same number? Let's do some Control Z's here for a minute. Yeah, it was. Okay. So now we're starting down lower, or smaller, so our in file doesn't have to be so big. And yeah, in file, out file. So in file, open in file, out file. Out file, and that would be end. Boop, tab. Okay, that goes in there. Do that. Da, 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 da. Okay, close. Read. Let's do a.close. Our damn handles. Close, close, decode, encode. Alright, so let's give that a shot. If all goes right, we should be able to go paste, encode. And then we should be able to go paste, decode. Alright, so now we are in this folder, so let's put this tiny JPEG, which is not that tiny, but it should fit, into what's the difference between, I don't know. What's OK2? Well, we'll just put it in there. So we're going to put this JPEG in that bitmap. And if we recall, we take a file path, which is what we're going to put it in, and then our message file, and then our out file. So ok.bmp sfi.jpg. Let me just go like this so I can see these. Let's do encode, and that's ok.bmp. Not like that. Okay, is that a dead pixel? Just found a dead pixel on my monitor suddenly. Son of a bitch. Anyways, ok.bmp and sfi.jpg, This is a really big file, so this might take a little while. And let's put that to JPG in BMP.BMP, of course. Done. And let's look at that. JPG in BMP. Can you see a difference? Because I can't see a difference. We just put a 50, almost 60 kilobyte JPEG inside this bitmap, and you can't tell the difference between that one and this one. I can't tell a difference. If you can, it's very subtle. Like maybe this hair's darker, but I feel like that one's bigger. Like I don't see a difference. Now let's see if decode works. And this is in file and out file. Now this one might be wrong because my math might be off, but we'll see. So decode, and that's going to be JPG and BMP.BMP and work.jpg. We know it's JPG, and we could identify it like if we just dumped it to a bin. Let's see. Still running. I wonder if my stuff was off and in here when we just did it real quick. Oh, we forgot to do pl.close. I don't know how many times that's doing that, but it's definitely still going. I feel like we need to manually do it again. Oh, it's done. OMG, look at that. Work. It worked. And lossless as JPG can get. Big file. It was, but did you see how much faster it encoded versus decoded? Why is that? The encode was like done. The decode, I think I know what it is. And it's that I'm doing a string here. I'm doing plus equal. And I'm doing a 2s on all of these. Whereas if I don't do that, because here we're doing 2i, 2s, 2. So here, let's see here, we're grabbing t, that one, 2s, 2. We need to do that. We're not adjusting. We do need the last one. Let's see if it's faster to, instead of add to a string, add to an array. Like that. And then do dot join pack. See if that's faster. That may not even work, but let's do a quick little test here. OK equals. It's gonna end up being 1 0 1 0 1 1 0 1 1 0. OK dot. Does this work? No. OK dot join dot pack. OK dot join. Yes, so that does work. So it'd be just like this. Let's see if this is faster. Decode, and let's call that work 2. There we go. Oh, damn. Worked too. That was so much faster. So what did we learn? Strings are really slow. Use an array and then join it to a string after it's done. Because joining them all is much faster than doing, here's a big string, add a character. Here's a big string, add a character. Here's a big string, add a character. And we can actually benchmark that. I've forgotten how to do a Ruby benchmark, but it's easy. Okay, dot join. Wow. Yeah, that was me too. I was like, whoa, much faster. Okay, so require benchmark. And then let's do this. Okay, so we got the benchmark and 50,000. Sure, that's good. That's respectable. Benchmark BM do x dot report. This would be for a loop. I want to do t equals. I don't know if it can see these or not, but we'll find out. T plus equal O. H equals this. H O. And then this one, of course, at the end. I don't know if I can do end join, but yeah, let's just do this and see what happens with this. Oh god. Unexpected keyword. And equals this. Okay, so I think we just do this. T equals that. T plus equals. No, it's gonna. I feel like it's gonna do this. Oh yeah. For. Okay, these need to be out of here. I'm stupid. We'll see. There we go. I think it needs a loop. Yeah, it does need a loop. I'm just stupid. And we are using an n.times do. Let's try this. Not for, but let's do n.times do. Does that work? Oh yeah, this doesn't go here. N.times do P, and we want to do P, and that would be T plus equal P dot 2s. Does that work? Is that proper? just do n dot times do p. I think that's right. And then just grab this. Do p, and this would be h. PHS. Is that correct? I don't remember, but let's paste it and see. No, it's not. Will a 4 work? Good morning. Okay, so let's just get rid of the P. And just, this is going to be quicker and easier anyways. Get that out of there. That was my fault. There we go. There we go. Running. Okay, so for this one, the string, it took fucking forever. Almost a full second to just do that, to add an O to the end of a string 50,000 times, and it took less than so pretty much what we're looking at here is 803 divided by 5. It's 160 times slower to add it to the end of a string. Well, hello there. Finally, the time zone worked out for me. Well, hello, James, eh? And you're catching the tail end of it, but this is where it's getting exciting. So we just learned that at least in Ruby, and probably everywhere, because if you think about it, it makes sense, that appending a character to the end of a string repeatedly is 160 times slower than just adding a character to an array and then at the end joining them into a string. So what we did was we created, we don't need the benchmark, an encode and a decode. And here's the encode. Let's grab that. Control Z, which is already in here. And decode is already in here as well. And now fixed. And let's show it off one more time for anybody that missed it. We'll go over the code, and then I'm going to bed because holy shit, it's 3:30 in the morning. So, bitmaps is what we're using currently. In C, yes, a string is a simpler array, but the way that Ruby handles them, because it's interpreted, it's going to load the whole string over here, add a character, save it over here. Whereas an array is just, okay, here's the end of it, throw it on. 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 And in C, if you tell it to do it with with a string, like if you do stir cat, imagine this. So instead of, okay, we have like 2 megabyte array of zeros, and we can use up to any of it, stopping at any 0, and we just iterate through it, changing the next one. If we, instead of just iterating through it and going, okay, this one's that, this one's this, this one's that, and just moving through it, and we did stir cat for each one, and went stir cat, stir cat, stir cat, it would go, and you'd be doing a function call every iteration of the loop. So fuck that. We just want to move through the memory every iteration of the loop. Okay, so let's see if we can, let's see how much we can cram in this. So we have a, let's put it to max. This is about 2 megabytes is going to be the upper limit there. So let's find something that's about 1.5 megabytes. Let me just go to my downloads folder, sort by size, and go to about the 2 megabyte range. What's this? What is VBR? Oh, VB Reformer. Let's put vbreformer.rar into OK.bmp. So, OK.bmp looks like this. We stole this off the internet. I just Googled hiding shit in images, and then it was originally a JPEG. I opened it in Paint, saved it as a bitmap because, well, JPEG is a whole nother beast. You got less file size to work with, and we would have to just probably just do it in the quality tables. But we did go over hiding strings in JPEGs in the last stream. Then it crashed, and then over here we found that there was a couple hidden strings in this. One was like, "What the fuck!" exclamation point. And the other one was like, "Okay." Maybe coincidence, maybe not. But that was the last stream. I hid some strings in the Benny Bills and wrote a little program to just spit out strings. And then this one, we converted this to a bitmap. So here's the JPEG, here's the bitmap. And now let's hide vbr.rar in there. Let's go up, grab our encode, which, let's see here. Okay, that's encode, decode, and we want to encode OK.bmp. We're going to change that. So we're going to do vbr.rar, vbr.rar, and let's call that rar in bmp.bmp. Now this one is probably going to take a little bit longer, although last time it was damn near instant. I'm going to put this right here. I'm going to make this a little bit smaller. Alright, so we can watch, and we're going to be looking for rar in bmp.bmp. No errors. Wrong number of arguments given. One. Okay, block and encode. Let's see here. $885. I think. 856. Times block in encode 2s. Wrong number of arguments given 1, expected 0, which means we got a nil somewhere. Let's go to 856. 856 is here. So 160 plus D. Our file is probably just a little bit too big. Because this... Let's try doing it manually real quick. Message file equals... Wait, is that megabytes? Did I... Yeah, 2.02. It's probably a little bit too close to too big because... Yeah, because essentially it needs to be 1/8. Because we're doing every least significant bit, so... Yeah, 1/8 of that. So we're using 1 bit per. Yeah. So 2 point. Let's see here. This in bytes. Okay. .bmp. How many bytes is this? Copy. Control V, minus 160 divided by 8. We can go up to, now this is technically bytes, 1024, .276 kilobytes, roughly. So we fit that in there. Oh, let's put the Benny bill. It's 245 kilobytes. Let's put the Benny bill in there. So let's do. Now, if we adjusted each, no, then it wouldn't maintain. But yeah, we're doing the least significant bit of all the bytes. We could do every word and get double the space. We could do thirds and get triple the space. We could get almost. So currently we're at about, what is that? 276 divided by, so that's kilobytes. This was 2.16 times 1024. So we'll say 2212. And what did I say? 276 divided by 2212. We're at about 12.5%. Now, if we did the least significant bit of each word instead of D word, we double that. And we go up to about 25%. So a quarter. And if we did third, it would be this times 3, which would be almost, well, we'd be at 38%. That's not terrible. And at that point, you'd probably see a little bit of a difference, but probably not much. We may have to look into that here next time. But let's get back to this. Let's put the Benny bill. Did I copy that? Now this is the Benny bill with the hidden message. So it's a hidden message inside a JPEG. That JPEG hidden inside a bitmap. And that's going to be BB and BMP. Now this is right up against the upper limit, so it might error still. We'll find out. Done. And you'll see that we have BB in BMP. Where are you? Right here. Now this contains this entire JPEG. All of the data for it is in here. And if we were to open it in HXD, move this over there, go to this. Now this is the BB in BMP. Let's go analysis, file compare with OK.bmp. Go, and you'll see that F6, all of these are different, starting with there, and this is going to go for a while, a long while. Now we can't really even see it, but it's there. Is there a way to go to last? Search, edit, analysis, file compare. Let's go to the bottom. And can we see anything different here? Probably not. Essentially, we want to find the previous view, file compare, previous difference. So look, we used almost all of the file. Wait a minute. No, click at the bottom, click the bottom. File compare, previous difference. There we go. So we are here, and that is the last E8, 9F. Yeah, so that is the last one. So we had a little bit more to go. But we used, like I said, about 80% of it. So we could get a little bit up there. But now the cool part. So we have this BB in BMP.bmp. And just to make things fun, let's go folder. BB and BMP. Let's go back. Let's just call it NF because I don't want to type for days. Grab this. Whoop. Grab that. Grab this. And we want to decode, and it's in file, out file. So decode. It's going to be this for in file. And oh god, I just overflowed it. There we go. Okay, so oh boy. Decode. It's gonna be this. For in file. And then slash out dot JPG for out file. And you son of a bitch. Oh, right. Damn it. Let's start with a notepad to make things easy on ourselves. Because we need to go like this because Ruby is, you know, fancy like that, and it will escape those. So there's our out file. Don't open it. Just do this. Control. And we could definitely go like the least significant 2 bits, or every other bit, and it would definitely be fine. I'm sure of it. We can improve on this. We can make it better. But the important part is that we've started it and we've finished a version of it, and we are testing that. And from there, you tune it up. So decode in file. It doesn't look like I've erased that, but I did. It's just my console is stupid. Out file, and it's going, and it's done. And bam, there's your Benny Bill in your folder right next to it. No trickery, folks. You saw it here, and so many people have already done it. Okay. Freaking awesome! Right? So we put 245 kilobytes into a 2.16 megabyte bitmap, which honestly is pretty big, but when you can write a keylogger in, I mean, of course you would have to extract it from something somewhere, but I could put this on Facebook right now and be like, here, check out this awesome image. It probably wouldn't preserve it. It would probably optimize it somehow, convert it or something, but anywhere that I could upload it and it would preserve that image type. And that's why if we get into PNGs and do this with PNGs or JPGs, where it's smaller and we can figure out a good way to just mess with like the quality or something, so it you can't really tell. That's when you can throw it up somewhere, and your buddies would be able to be like, yeah, anytime he puts a picture up, run the decode. There might be something cool in there. You never know. You know, I could drop this in Discord. I'm gonna drop this in Discord right now. No, not yet. I'm gonna put a file in it. Let's go to this PC. Oh, so much free space now. D drive, coding. Oh, check this out. So project C. So these are all the actual files. Now, I did almost lose that hard drive, and here's F, here's recovered D, and you'll notice that now, since I've gone through this, project C, a lot of these, if they're big enough, are all going to be just sim-linked. Make a liar out of me. Well, I went through and did it, and a bunch of them actually are now, but anyways, back to this. Let's see here. We do have a keylogger. I think it's called KLGR. Let's take a look at this. I don't know what that was all about, but go into text, foreground rendo, translate, cool. Download C drive WP. Okay, okay, this submits it to a web URL every so many big sized, so 127 /t blah. Be right back. Dog behind me freaking out. There we go. So every 1024 characters, it will do a GET request to a web server with all the logged keys. Execute. Let's do project options. Let's see here. Compiler, linker, strip executable. And this is a Windows program, so it won't create a window. So we should have a call next hook, callback, send log. Oh, okay. This is an old send log. Convert, unlock my, okay, WinMain. Let's see, it should have a WinMain. URL download file, and let's go compile. It compiles just fine still. I don't remember when I wrote this, but there is a tutorial on writing one kind of like that. I think it's this one. Yeah, this one just prints it to the screen, so you're keylogging yourself. Can I open file? Yeah, I don't care. Close yourself. What? Oh, not you. There you go. So put that up there. Be like, I'm typing here. Right. So this one doesn't have any conversion for characters. It's all going to be in caps. It doesn't check the scan code. It just reads the character and it prints it out there. All right, Universal, see you later. Thanks for stopping in. The other one actually doesn't print it, but this is, yeah, uses a hook still. But we will put the good one if it's not too big. I'm sure it's not, because project, it is 11 kilobytes. Woo! So project one, oo.txt. What is this? Let's see here. Oh, that's a log file. 312 kilobytes. That might contain passwords. Oh, no. It is log file, and it could, but it's all in hex. Yeah, I think that was a binary patch of mine. Anyways, yeah, 78 kilobytes, not sure what that was. But let's grab that. Let's go ahead and go back into, not here, let's close this. Let's go back. Alright, so we're going to get rid of this. And we're going to put this here, project 1. And let's, oh god, that breaks it. Encode, I'm not going to put it in another folder, because as long as I don't go into a different folder, I can just type here. So project, not project 1, but ok.bmp. OK.bmp, and in file, which is project1.exe. Out file is find, I don't know, let's see here, let's call it findme.bmp. And let's move this over here, and we should be able to see how quickly it encodes. It's gonna go quick. I mean, 11 kilobytes would be easy. Done. Find me, boom. And there you go. Do you see the executable for a keylogger in there? I don't. Of course, it wouldn't run unless you did some really awesome trickery in there that somehow overflowed something like a bug in a bitmap viewer or something like that, that then ran code that collected all those, put it together, and then ran that. Like, it's harmless. You've binary encoded the least significant bit to have your program in it, but now you could share this with your friends, and only the people that know how to get it would be able to go like this: decode findme.bmp to foundyou.exe, and we'll see, boom, foundyou.exe. And if we hxd one more time, we'll see that that is all there, and it's the same as this, all the way down to the very last byte. And I'm going to go ahead and put that in stream. Let's see here. Where should I put that? I'm going to put that in coding challenges. I'm going to put the... Actually, I'll do you one better. The executable doesn't really do you any good. Let's put the source of it in there, which is this guy right here. It's even smaller. Can antiviruses? No. An antivirus is not going to detect it because it's not runnable. Like, you can't, you wouldn't be able to put this as .exe and run it. It just wouldn't work, like, because it's not, it doesn't have the right header, and the bits to make the exe are not in that order. So, but if you found an exploit in something that you could then, like, scan the hard drive for one of your bitmaps that happens to contain a payload, or some other file that scanned for this later, found it, and then it was like, oh, this matches the hash for my thing that contains a keylogger. People always saving my images. I told you not to save my images. And then you activate, it pulls it down and runs it. You know, I mean, that could be possible. Of course, that wouldn't be very ethical, but you technically could do something like that because the file is there. It's, you just have to know how to find it. So let's put the source in there, including all of my, maybe including all of my, let's see here, did I paste it in here yet? Control V. So let's take out my big heaping chunk of comments. Save. Okay, so let's go encode OK.bmp main.cpp. There we go. So we've replaced find me, and let's go decode find me with foundyou.cpp. And let's main.cpp, found you.cpp, found you, and what do you know, there's all the source. And I'm going to put find me in the coding challenges. There is source to a fun little program hidden in this. Hope you saw the stream. Upload. So, the source to a fun little, I mean, nowhere am I going to advocate, using a keylogger for any type of malicious purposes, but, if, like, personally, I put one on my own computer so that when I'm gone, it can activate if other people are on here typing. I know what they did, I know where they did it, because this will grab the window title, what was typed in that window, and then anytime the window switches, it will add to that window title, and then when it gets so long, it sends it to a server, which I can read those logs. It's encoded. I don't remember if I encrypted it or not. I'm sure I did something, and then I can read it from my phone or any other computer or something like that. So if I start getting logs, I'm like, oh, somebody's on my computer. And I may or may not be able to send myself an email that just turns it off over and over. Or changes the password in the background and then turns it off. Things like that. Of course, I would never really need to do that now. Because I don't care if people use my computer. But say I got home and like things weren't acting right. I could look at that and be like, what was typed in? What was clicked? What programs were ran? Okay. So, I mean, source for that is in there. It didn't display it as an image, I think because I drag and dropped it. I wonder if I copy paste it. Find me. Is this... That doesn't do it either. What the... Paste? No, that doesn't do it. So bitmap, it doesn't show it as that. Probably because it's too damn big and nothing displays bitmaps anymore. But let's see. Can I do new text document? Test.html. Edit. Let's do HTML. What? I feel like there's a bug crawling on me or something. Ha! HTML/HTML, head, slash head, body, slash body, image, src equals find me dot bmp. Don't think this will work. Yeah, it does. So I could just display that. Let's do that. I'm going to put this on my server real quick. I swear there's like a bug or an ant or something crawling on me. Piss me off. Close that so I can see stuff. But yeah, I once wrote a program that would take a bitmap and convert it to HTML. Like, it would create a table and each cell was a pixel, and it would encode that cell with the color of the pixel, and you could watch this image just take forever to, basically like back in dial-up days, loading an actual image, and it would do that, just loading this bitmap super slow because it's filling in a cell for each pixel of it, and you're like, this page is 27 megabytes. Oh, there's a picture. Cool. You displayed a picture. Yeah, but it's all text. yeah, you could just, PNG and code it, base64, all text. No, this is code. Like, the code is generating the same thing you see. I mean, I grabbed the width and the height from the file, set that in the table, TRTD, for loop for each little pixel, encoded the colors for it. Bam! It was fun. Maybe we'll rewrite that just because there's somebody out there, some kid that is thinking about that or hasn't thought of it, but it's a decent thing to do to kind of get your feet wet. It's fun and it makes you think. Anyways, let's get out of root. /var academy. This won't stay here, but we'll put static find test and find me. And then we should be able to go give.academy if it's still up. By the way, if it ever just randomly disappears, yeah, sorry. Long story short, I registered the domain with a certain company. Certain said company wanted to charge me an extra $100 for no good reason. I told them no. And then they tried to say it was due to this and that, and I was like, well, that's your own fault because I had auto renew and it renewed. My card was lost or stolen. I paid you, and now since it was like a little bit late, you want to restore fee me for $100, but it didn't even suspend until 2 days after I paid you. GFY. And so I talked to a supervisor, and they're like, oh, okay, we'll apply credit the account, so that'll go away. And then they charged my card for $100, so I charged it back. And so then they were like, oh, well, you're locked out because you did a chargeback. And I was like, yeah, you're supposed to credit my account that, and you charged my card. So, what? And so I'm just sitting and waiting to see what happens. Nothing. I don't see anything else to do with it. But it is currently up. Inspect. Findme.bmp is there. Except it's case sensitive, and I put a capital. Gotta love that. Refresh. Okay, so you can all see it right there, which this is right here. Will it display that or not? I don't know. Let's go open image in new tab, and it downloads. Let's go copy image address. Delete. Alright, so now there's a link. You can view it. It displays online. And if you go back through the video and you look at this code right here, this is encode. This is not every third byte. Encode. Just leave that right there for a minute because you're going to have to type it. I'm going to make you think. I'm going to make you be the 6, 7, 8, 9, 10-year-old self of me reading out of books and going, typing pages, like pages. This is nothing. I would have been happy about that. Pages of like basic or C. Just to go, damn, it doesn't work. Where's my typo? I'm gonna make you live through that because that I miss it. It was epic actually. And finding good books like that is actually either it's either hard to do or more people are just putting it on the internet, or I haven't looked hard enough, which could be all three of those. So there's the encode. Of course, you can pause it, and here's the decode. But yeah, you're gonna be, anybody who wants to do this is gonna be that small self of me who had it started out a basic book, and I was reading line by line. Oh, I want to draw this box on the screen. All right. And it wasn't like this. No, it was. In QBasic on DOS on a 486, and then F8, syntax error. What does that mean? Yeah. So there's the decode. We know that these work, and I'm actually going to save this file save as, because I haven't saved it yet, and that's a bad habit of mine. But you know what's really awesome about Notepad++? If you close it, notice it didn't prompt me to save. Notepad++, it saves them in, temporary files somewhere, and it will recall it automatically. I use that because sometimes my computer hard locks, and I don't want to lose all my coding or whatever I've done in here. So now I am going to save it. This is what I do when I want to keep it forever. And this is going to be encode, decode, BMP, stenography, steno.rb. Alright. Oh, I should be real mean and do like my decryption challenge and put the source inside a picture and be like, here you go. If you get it, you get the source. But if you get it, you don't need the source. My decrypt me challenge. Let's see if I can find that. Decrypt me. Good luck. This right here. Decrypt me. Good luck. And it is the source for encrypting and decrypting files like this. And yeah, there is one caveat, and it is that I used this symbol right here, and that symbol could come up. Now, if you want to see the code to that, I don't know if I still have it. I might have to rewrite it again just to get that, but I think I have it in fucking important. That's a folder on my computer. There it is. Decrypt me. Nope, that's not it. This is like revision 2 or something. Maybe? No, that's not it. Let's see here. Text. Dishwasher. Faucet. No. Keys and private keys. Don't open those ones on stream. Oh, that's fun. Yeah, print the first argument and whether or not the second one is no. Cool. Close that. Open. I think this is it. Nope, that's another encrypted file. Open. A codes TW. It's gonna be bigger than that. It's gonna be. Symlinks. Oh, those got moved. Okay, that's fine. Where did I put it? Maybe it is on desktop. One byte runner. Let's see here. I want star.rb. Nope. Star.txt. That's not, ouch. That's not it. Open. Comp nodes And settings, oh, that's not it. Go back to the desktop. Star.txt. Oh, there it is. I found it. Ink deck mine. Encrypt, decrypt. Oh, this is just the notes. This isn't even the source. This is my notes on how to make it. Oh no, this is the tutorial on how to make it. So yeah, read binary data. This is text. Put length by followed by @ See @ that's a downside. Should never do that because that's a character that could come up in here. And then you do this, and then you do this, and that's how you encrypt it. And if you know how to encrypt, you just do the backwards to decrypt. So there you go. And encrypted decryption looks like that, which is just, it's right there. I mean, that decrypt me is in there somewhere. I put it in here somewhere. I think I put it in coding challenges actually. Yeah. Maybe, no. I don't know, I put it somewhere for cat a long time ago. But, guys, it is 4 a.m. I am going to bed. So, thanks for watching. You guys have a great night. I will as well. Thank you much. That was fun. A little bit different. Obviously, we weren't reverse engineering, but one of the biggest parts of reverse engineering is learning to think in a different way. Think outside the box. Think of, if I was going to do this, how would I do it? And then what would it look like when it was done? Then go backwards. So big part of any reverse engineering is persistence, looking shit up, and thinking outside the box. So if you're new, thanks for watching. 3-hour stream. Rate, comment, subscribe, share, all that stuff. Honestly, pop into the Discord, throw some ideas my way. This idea was inspired by the Discord there. And beyond that, I'm going to get some rest. See ya. Thanks.